In this video, we're going to look at rate of change, both average rate of change and instantaneous rate of change as an application of differentiation. So the average rate of change is the gradient of a line joining 2 points. So you'll be asked to find the average rate of change between x equals A and x equals B. So it'll be 2 points, P and Q. And so the gradient of this line here is your average rate of change. And to find the gradient of the line, we use the difference between the y values divided by the difference between the x values. And it doesn't really matter whether you use f of x2 minus f of x1 or the other way around, swap those two around, as long as you have, if you've got 0.2 values at the start and 0.1 values at the end, or vice versa. So they have to match. You can't have a yellow one at the top over the top of a green one, if you like here. So whichever way you go, you'll get the same answer. The instantaneous rate of change is the gradient of the tangent at a particular point. So at this point here, we find the gradient. That's our instantaneous rate of change. It's also the value of the derivative for the function evaluated for that particular x value. So what does the rate of change tell us about a function? If the rate of change value is negative, then the quantity that you're measuring on your y-axis, so down here, if the rate of change is negative, then this quantity here is decreasing. If the rate of change is 0, then your quantity is unchanged. And you'll often see this used in the word with the word for speed, for example, at a constant speed or a constant velocity. It is unchanged. Obviously, if the rate of change is 0, then that means that the derivative is 0, and so you have a flat line. If the rate of change is positive, then the value on the y-axis is increasing. And the larger the value of the positive value, or the more positive it is, or the more negative it is, the greater or faster the rate of change. So if you have a really steep slope that will have a high positive value, then you have a fast rate of change. If it's kind of flat like this one, you'll have a slower rate of change. And so for this graph here, we're looking at dollars per year. We're looking at a profit formula here. And so the formula for this line, y equals 2x plus 5, the gradient is 2. Our quantities for our gradient are, of course, our y value over our x value. So if you think about this gradient here, it's the derivative of y with respect to x. And so our y value units go on the top, our x value units go on the bottom. And if you wanted to describe the rate of change for this function here, you'd say that the rate of change is increasing at $2 per year. And our rate of change units are always said as y units, whatever the units are for your y units per x units. So if you've got meters cubed up here and years here, it would be meters cubed per year. Sometimes one of the things that you're asked to do is to find a maximum value or a minimum value for the rate of change. Not the function itself, but the rate of change of the function. So for a function f of x, the rate of change of that function is the derivative. And so what the question is asking you to do is, for this particular function here, if you're asked to find the maximum rate of change, so the rate of change is the slope, so it's asking you, where does the slope of the line have its maximum value or its minimum value? Where is the slope of this line a maximum steepness or a minimum steepness, if that makes sense? So to find the maximum or the minimum rate of change, you're looking for the the steepest or the less steep point on the function. And so this point here has a zero derivative, a zero slope. However, this point here, if we're looking at a minimum, this point here has a negative slope, which is more, a negative value is more negative than zero, and so we'll be looking here somewhere at this particular A value to have the minimum rate of change. Our maximum rate of change we would be looking for somewhere along here maybe, where the tangent is as steep as possible. So for a maximum rate of change, you're looking for the maximum value for the derivative function. So normally what you would do would be to sketch the derivative function and have a look. If you're after the minimum rate of change, you're after the minimum value for the derivative, or in fact on both of those things we could have the word slope. So to find the maximum rate of change, you find the derivative of the derivative function. So maximum gives you the derivative of something equals to 0, and you're finding the maximum of the rate of change, and the rate of change is your f dash of x. Then you solve that function for x to find when the maximum or minimum occurs. So that will be like our a value that we found here, and then sub that x value into the derivative function to find the value for the maximum or minimum rate of change. Let's do a question that'll involve that. So let's look at an example. The volume of water in a tank, here's the tank here, measured as V litres, is monitored for 8 hours. The function v of t, this formula here, for 0 is less than or equal to t is less than or equal to 8. So between 0 hours and 8 hours can be used to describe the volume. So the amount of water in here is measured for 8 hours, and this formula describes how much water there is at any given time value. So the question then asks us, what is the initial volume of water in the tank? So initial volume means the amount at the start, and it will be the amount at the start of our domain. So our t value is going to be equal to 0. Then it asks us, what is the rate of change in the volume? So rate of change, it's asking us for rate of change in the volume. So it's asking us for dV dt. The rate of change in the volume at the start of the 3rd hour, and then at the end of the 3rd hour. So we'll investigate this in a little bit, but this is actually different. This question is here so I can show you something. And then finally, when is the rate of change, when is the rate of change the greatest? So when is dV dt at its maximum value? All right, so let's go ahead and do some of this work. So for part A, what is the initial volume of water in the tank? So the initial volume of water is when t is equal to 0. And so what we do is we substitute a 0 for t in our volume formula. When you simplify that, when you simplify that, you get 256, and then we answer the question. Okay, so the initial volume is 256 litres. The question didn't ask us what V0 was, it asked us what the volume was. So when you're answering these questions, you need to answer the question. And so you can either do stuff like put a box around it, put your units on there, Okay, so your units are really important. The other thing that you can use is some notation that shows initial volume. So V with a little zero sitting next to it actually stands for the value for V. So you don't have to actually write the words initial volume, just write 256 and an L, put a box around it so that you show that that's the final answer. The second question asks you for the rate of change at the start of the third year and the third hour, and the end of the third hour. So this is here specifically so that I can show you something to be careful about when you're working out when your time period is. So you can see over here I've got the first hour, the second, so hour number 1, 2, 3 and 4. So they are counting the time periods, but when you label first, second and third, this is the first second, this is the first hour, this is the second hour, and this is the third hour. So at the start of the third hour, you're actually talking about this Y value. And at the end of the third value, you're actually talking Y value. You're talking about this X value. So at the start of the third hour, X is equal to 2. And at the end of the third hour, X is equal to 3. So any time that you're working with time and it asks you things like at the start of the first year, at the start of June, at the start of the third hour, and they're labeling it as first, second and third, not using T equals 1, T equals 2, T equals 3. Make sure that you check this idea here so that you're actually working with the right X value or the right T value, the right time value. Anyway, so to do this, we're going to substitute X is equal to 2 and X is equal to 3. The question asks us for the rate of change, so we're going to substitute those two values into the derivative of the V function here. So the first thing we need to do is collect the V value to find the derivative. Now this is in fact a chain rule because you've got a function inside a larger function. So our inner function is 8 minus t and our outer function is this to the power of 3 function. So we do the derivative of the outer with the inner still as it stands and then multiply it by the derivative of the inner. Once we've done that, we'll have our formula for V dashed, and then we can, so this is our formula for V dashed of t, and then we can substitute in our t of 2 and our t of 3, and you can see that I have ended up, and this time I've just thrown the litres per hour on the end, and if I box it up like that, that will be enough to get you full marks on the exam. And finally, part C asked us to find when the rate of change was a maximum. The rate of change was a maximum. And so what we need to do is we need to find the derivative of our rate of change formula. And our rate of change formula is V dashed of t. And to find a maximum or a minimum, you let the derivative equal to 0 and then solve it for t. Okay, hopefully you remember that from year 11. And so the first thing we need to do is to find the derivative of our rate of change formula. And so we just treat our rate of change formula as if it were a normal function itself. So again, we've got an outer function and an inner function. So we've got a chain rule here. So we find the derivative of the outer function with the inner function still as a whole. And so we had a power of 2 here. So this will drop to a power of 1, which I've just left as not written there. And then multiply, of course, by the derivative of the inner function to give us minus 1. And so now we have a new formula for our rate of change of our rate of change. And so if we set this formula equal to 0 and solve for t, we get that t is equal to 8. So we've only got one value for our function here. Sometimes when you solve to find maximum and minimum, sometimes you'll get 2 or 3 or 4. We're told it's a maximum, so because there's only one value here, that one value must be the maximum value. And so we can answer the question, maximum value when t is equal to 8 hours. Box that up at the end, question done. This final example I want to go through because it is similar to an exam question that's popped up a couple of times in the past. And if you haven't looked at similar triangles for a while, you'll really struggle to actually even start this question. So if you walk through it once, you'll be able to do it with all different sorts of questions. So here we go. A container in the shape of an inverted cone, an upside down cone, with a radius of 2 meters and a height of 5 meters, radius of 2 meters and a height of 5 meters for the cone, is being filled with water. If the depth of water in the cone is h meters, so this is the water level here up to the blue line, so the depth of water is h meters, find the radius r meters of the surface of the water in terms of h. So we want to find that radius value there. And we've got, in terms of h means our answer for this r value is going to have a h in it. Then we need to show that the volume of water is this amount here. And then finally answer the question, what is the rate of change in the volume of water with respect to the depth, so h meters, when the water is 1 meter deep? So when the water is 1 meter deep, how fast is it changing? What's its increase or decrease in what units have we got? Meters, and our time is measured in, our volume is meters cubed and our depth is meters. So our units are going to be meters cubed per meter. Interesting. Anyway, let's have a go. So to find R in terms of H, you need to go back to your Year 9 work on similarity. Now, this is assumed knowledge. This is assumed knowledge. It's not on the formula sheet at all, similar triangles. And like I said, if you can't remember them, if you can't get it right, then you can't do the rest of the question. You'll stop at part A or miss part A here. This question, part B, the show that, helps you to move from here onwards. You still won't be able to do this if you can't find the first one. Okay, so like I mentioned already, we're going to use similar triangles to solve the first question. And we actually have two triangles here. One that is made from my yellow values, which is the cone. So I've taken this height here, and instead of measuring at the side, I'm measuring down through the center and then across to the side. So I'm creating this right angle triangle here that has, at this point, this particular angle here. Then I've done the same thing with the green lengths that I'm measuring here that also share that same angle. Now the top of the cone is at 90 degrees to the line down the center, so that's a right angle there. And then the top of the water is at 90 degrees to the line directly down to the bottom of the cone. And so what we have here is that these two these two triangles are similar because they are right angles. They contain a right angle. They have the hypotenuse is the same slope, and one of the angles is the same. So they are similar RHS. I can't remember exactly what that stands for. I remember it as they're right angled triangles with similar sides. So what we can do with our similar triangles is use the scale factor for these two triangles. And the scale factor goes, if we do 2 divided by 5, we will get the same answer as if we did r divided by h, because it's like a blown up version. It's increased by the same amount. We don't need to find the amount that it's increased or decreased. We can just say that this 2 divided by this 5 will be equal to the equivalent side on this one, which is r, divided by the equivalent side on this one, which is h. So you must match up the sides. So this is the adjacent side to this angle, so that will match with the h. Okay, I hope that makes sense. So these must be in the same positions in our fractions. So from here, we get, if we cross multiply here, multiply both sides by 5, multiply both sides by h, we get 2h is equal to 5r. We could also do similar triangle pattern using the fact that this side is a particular value. Well, let's start with the r. If you multiply r by a particular amount, you'll get 2. And because the whole thing's blown up the same amount, or increased, enlarged the same amount, you can do h times by the same amount will give you 5. And so you can see here that I've got these two sides are the same, and these two sides are the same. Again, large triangle on the top, small triangle on the bottom, but you end up with the same relationship. So my suggestion would be that you put this in your bound book. Put this in your bound book. Something about similar triangles to remind you how to do them. While you're at it, if you need to throw in the old right angled triangles for trig, they've used those as the basis for a differentiation question before, as well as some assumed knowledge from geometry, circle relationships and stuff. We'll talk about those more in another video. All right, so now we've got a relationship 2h is equal to r, and what we need to 5r. So what we need to do, this is my working out over here now. What we need to do is rearrange this so that we get r in terms of h, which is what we were asked to find. Put a box around it, done. The next question asks us to show, what does the next question say? Show that the volume of water is this particular amount here. Now the volume of the water you need to work out, it's the shape of a cone. And immediately you're going to go, oh my God, I don't remember what that is. But in the past, they haven't asked you to try and recall. The formula for the volume of a cone is in fact on the formula sheet. So this is what it looks like on the formula sheet. Volume of a cone, that's what it says. And in the past, where they've used formulae like this as the basis for a question, they've had those there. So have a look on the formula sheet to see what geometric shape formulas, volumes, surface areas are there, and then add other stuff to your bound book that's not on the formula sheet. So we have that V is equal to a third pi r squared h. That comes from our formula sheet. We know that our r value is 2h on 5, so substitute that in. Expand the square. Oh, come on, roll down. And you will need to tidy it up so that it looks like what you were asked to find. So it's a show that question, and there's two reasons they'll do a show that. One, to get you to do some algebraic manipulation so that they can test that, and secondly, so that you've got what you need to continue on part D, E, F and G. But because it's a show that, you need to show clear logical steps. Okay, so you need to start with a basic formula, substitute in and then rearrange. If you don't show this, you won't get the mark for the show that, because there's no marks for the final answer. The mark is for this. And in this case, probably substituting that in with clear working. I hope I emphasised that enough. Show that clear working. Right, part C, the rate of change of the volume with respect to the height. So we have our volume formula. Now you can see why they gave us the volume formula, because now we can, even if we couldn't figure this out before, we've got a volume formula to work with. So if you come across a large question, one of those extended response questions, and it says that there's a show that question, I will guarantee you that show that is used in the next question. So don't get to a stage where you can't show that and then you stop and don't try the next questions. Always check to see, can I use what they've asked me to show in further questions, because generally you can pick up from there and move on. So there's our derivative formula. We're working with respect to h, and so h is the value that we're using our derivative pattern on. Pi is just a constant. Okay, so it doesn't get derived. So we've got h cubed becomes h3h squared. Simplify that when h is equal to, and then substitute h is equal to 1, because we were asked to find it when the height was 1 metre. When the height was 1 metre, substitute that into the formula, simplify it down. Now whether you leave your answer at this stage or whether you simplify to here will depend on whether they ask you for it in a specific form. If you give an equivalent answer, they accept equivalent answers. It says in the examiner's report, equivalent answers are acceptable. But note this, the question did not specify decimal points. If the question doesn't tell you to 2 decimal places, to 3 decimal places, then you don't put it as a decimal. You leave it as exact. Finding this exact answer, and then working out that it's something or other in decimals, does not get you any marks. In fact, it will lose you the final mark, because they are looking for, it says in the exam at the start of the sections, if you read the little blurb at the start of the sections, it says, unless specified, answers must be given as exact values. If you then go on from an exact value and you write a decimal equivalent, you're not giving the answer in the required form, and therefore you don't get the final answer mark. So the idea being that you've gone on, they call it further engagement. You've gone on and further engaged beyond what you were asked to do. And so the examiner doesn't know whether you knew that you needed to stop here or that you thought that this was a more exact answer. This is in fact more exact, so leave it. I hope I've said that enough. Don't give decimal place answers unless you're asked for them, or unless they are exact. So if you've got something like 5 on 2, it's okay to write it as 1.5 because that is exact. But this has an infinitely recurring decimal value, and so whatever you've got will be rounded off and it will be wrong.